So hello everyone, we are going to start with our next chapter, and the name of the chapter is binary search tree. So in the previous session we have studied binary trees, we have seen the concepts of binary tree, and we have solved a lot of problems in that. Now we are going to study another. You can't say that this is another data structure. It is very similar to binary trees, but you can say that this binary search tree, the concept of binary search tree is a much more evolved concept, is a evolved version of binary trees. And how you can say that this is a evolved version of binary trees? Based on the, like you can say, operations that we generally perform. If you perform on a general binary tree, then the operation, let's say it is taking some x time complexity. Now if you perform the same operations on a binary search tree, then it will take much more less time when compared to a general binary tree. So a binary search tree is nothing but a evolved version of binary tree. In binary tree we have certain properties, right? The properties are that for a given route it should have at max 2 branches. If a particular node, if a particular route is having more than 2 branches, then it is not a binary tree. It can have 0 branches, or it can have 1 branch, or at max it can have 2 branches. This is one of the properties of binary tree. Similarly, binary search tree will also have the same properties, but along with it, it will have some extra properties, and because of this extra properties, it will become much more efficient data structure. This is a much more, BST is a much more efficient data structure, and whatever the operations we perform, let's say I am performing search operation, so its time complexity will be much lesser when compared to a general binary tree. Let's say for a general binary tree I am getting a time complexity of big of n for a particular operation, and this n is nothing but total number of nodes present in my binary tree. Now if I perform the same operation in my binary search tree, then the time complexity will be big of h, and h is the height of the tree. So you can see that in, let's say, total number of levels are 3, so the height will be 3. For that particular height, what is the height of the tree, that will become my time complexity big of h. Whereas the total number of nodes, there can be 50 nodes, then my time complexity will become like greater for a general binary tree when compared to a BST. Because of this property, because of this efficientness and less time complexity, we use this data structure whenever we are performing rapidly, or you can say for a particular case, for a particular example, we have to perform again and again searching operation, right? So for that particular scenario, what data structure we will use is, we will use binary search tree, because for a hierarchical data structure we are performing searching operation again and again, and we know that the time complexity of BST is much more efficient when compared to a general BST. So because of this property, I will use for fast lookup. Now if I want to perform fast lookup operation in a particular node, then I will use BST. This is a concept of BST. This is why we use BST, because of its efficientness and the lesser time complexity when compared to a general binary tree. Now what are these properties? I said that we add, along with the properties of binary tree, we add some additional properties, and because of this combined properties, a BST becomes much more efficient. Now what are these properties? So the properties of BST is that for a particular root node, its left tree value, whatever the value I am getting on the left tree, those left tree subtree values should be less than my root node, and whatever the values I am getting on the right side of my subtree, those values should be greater than my root node. This is the main property of a binary search tree. Now along with it, there are certain properties you need to remember, so let us talk about those properties. So talking about the properties, the first property you need to remember in your head, in your mind, is that a binary search tree, a BST, is first of all a binary tree, right? So the first property is binary BST is a binary tree. This is my first property. And the second property is that left subtree node values should be less than my root node value, right? And the third property is that the right subtree node data should be greater than my root data value. This is my third property. And the fourth property is that for a given node, whatever the right subtree may be, whatever the left subtree may be, if I see for this particular left subtree, I am considering this left subtree as an individual tree. If I consider this left subtree as an individual tree, then this LST, this left subtree, should follow the properties of BST. This right part should follow the properties of BST. If any one of these are not following, then my whole tree will not become a BST. These are the four properties. The first is it is a binary tree. The second property is that the left node values should be less than my root node. The third is that the right node values should be greater than my root node. And the fourth is that left part and the right part of my tree should follow the properties of BST. Now I have taken the example, I have shown you the example of a BST. If you observe this BST, this is my main root value. This is my main root, right? Now if I observe the left element present, left node value present on my main root, the value is 2. It means that the root value, the left node value is less than my root node. Yeah, condition is satisfied. Now if you consider these two as a subpart, as an individual node, then for this its left part again is less than its root value and its right part is greater than its root value. It means that for this main root, the left subpart is a BST because it follows these two properties, right? Now after that, if you observe for this right part, it is greater than the root value, and this, if you consider this as an individual root, this root value is less than its right part. It means that the right side of my RST, this is right subtree, right? Right subtree is also following the properties of a BST. Because of all the properties are satisfied, this given structure, this given tree will become a BST. These are the properties of BST. Right, I hope you have understood what is a BST and what are its properties. Now let us talk about a special case, the special property of BST that you need to remember, and this might get used in a lot of time when you are like solving the questions of BST. This property will help you a lot, and the property is that if you perform in order traversal for a BST, then you will get the elements in a sorted order. And what is in order traversal? If you remember the you can say rules, they are like different rules for different traversals, right? If you remember the in order traversal, it says that go to the left element. After it, print the root value. This is the first part, is that go to the left side. After it, second one, print the root element, and the third one is that right side, go to its right side. These are the three values. Now if you apply in order traversal for this particular tree, if you apply, then my output will be 1. First of all, I am printing the leftmost element. After it, root 2. After it, rightmost element 3. After it, again left is completed. Now main root 4. After right part 5, 6. So you can see that I got my output. If I perform in order traversal for this given tree, then my given elements as I get in my output, those elements are sorted in ascending order. And if the elements for a particular tree are sorted in ascending order, then it is an indirect implementation that it is a BST, it is a binary search tree. So I hope you have to remember this property, that is for a given tree, if the elements of in order traversal are coming in sorted order, in ascending order, then those given tree, that particular given tree is a BST. This is a special property. Along with those four properties, you need to remember this also. Now moving on, let us talk about search. Let us talk about search now. So I said that for searching a particular element, if you search the same element for a general binary tree, it takes a lot more time. The time complexity of that thing is much higher when compared to a general like BST, binary search tree, because binary search tree will search, or generally it does perform operations in a much lesser time complexity. Now let us talk about how the concept, let us talk about the concept. We'll talk about the code and overall thing later, but let us talk about the search or general operations that we generally perform and how it is much more efficient, how or what makes the search much more efficient. Let us talk about that in detail. Now before we go into the operations of search or whatever the things that will take or happen in the search operation, let us recall one thing, right? In arrays, in linear data structures, we have studied searching algorithms, right? We have studied two searching algorithms. One is linear search and one is binary search. Another one is binary search. Now if you see binary search, what we are doing is that, let's say there are elements 1 2 3 4 and 5 6, right? Now in linear search, what we will do is we will iterate through each and every element, and as I iterate, let's say my key value is here, my key value, what I can take, let's say something 3. Now if I find this 3, then what I will do is that I will break out of my loop, and if my key value is present at the last element, then that will become my worst case, and for this worst case the time complexity will be big of n. And in binary search, what we used to do is that, let's say this is my array 1 2 3 4 5 and 6, and this is my key value. Let's say this is my key. So what I will do is that I will break my array into two different parts using my mid element. Using my mid element, first of all I will calculate that mid is equals to starting plus ending divided by 2. I will calculate mid. After, if my key value is less than my mid, then what I used to do, I will go to the left part of my array. So I will go to the left part of my left side of my array. If key is greater than the mid value, it means that I will go on the right side of my array. So I will go on the right side of my array. If k value is equals to my mid value, then I used to print the index or whatever the element, that element is present, I used to return true, or I used to return its index. So this is the concept of binary search. Similarly, in binary search, what we do is that the user will give me a key value. Let's say the key value is 3. For this particular tree value, the key value is 3. Okay. Now what I will do is that, let me remove this. First of all, let me remove this binary search and linear search. Now let us consider that for a given binary search tree, this is my binary search tree and this is my key. Now what I will do is that, in order to search a particular element, I will check whether my key value is greater than my root value. If it is present, then in arrays, what I used to do, I used to go on the right side of my array. Now here what I will do is that I will go to right side of my tree. I will go on the right side of my given tree. So I will go on root dot right side, right? If key is less than my root node, then what I will do is that I will go on the left side of my tree, left subtree, root dot left. I will go on this side. So let us write on this thing that this is my root node, right? And this is my key value. This is my key. So what I will do is that I will check whether my root value is less than my key value, right? Yeah, you can see that here the key value is 3 and the root value is 4. So what I will do is that I will come on the left side and I will check for this particular left tree. I will check. So for this root, the root value is 2 and the key value is 3 now. So I will check. If it is greater, then I will go on the right side. Now my key value is greater, so I will come on the left side, and for this particular subtree I will check. Now the root is 3 and the key value is 3, right? So here the k is 3 and the root is 3. If both are same, then I will print its data, or I can print its like the element is present in my tree, I will print true, or else I will print false. So this is the overall approach of binary search in my BST. And you need to remember one thing is that here for BST is much more efficient when compared to a general binary tree. Now let us talk about the strategy. Which we follow in solving all the questions which we like going to follow in this session. So in this BST, in the whole chapter of BST, we are gonna use the concept of recursion, and we will break our tree into different parts, left part and the right part. And let's say our problem is huge. Now for a given tree, I will break and try to solve the solution for its left part, and I will try to find the solution for its right part, and by combining these two I will get a universal, or you can say a final solution. So this will be my approach. Let's say this is my tree and it has some left part. Let's say this is the tree I'm having BST and it is having some elements, right? This is my BST. Now what I will do is that I will break this tree, I will break this into subparts, and for this subparts I will try to find the solution. I will try to find the solution for the left part, and I will try to find the solution for the right part, and I will somehow, after finding the solution, I will return this to my main function. And I need to keep faith on my whatever the function I am creating, whatever the techniques I am using, I need to keep faith on my recursive function that it will give something. And after keeping faith, along with keeping faith, I need to keep on one thing in track, that is being very clear what will be my base case. If we are not clear with my base case, then I will go into some, you can say, infinite looping or infinite recursion call until my memory gets full, right? So I hope you have understood. And recalling the some concept of recursion, that is I will break it down for my left part and right part, and I will keep faith on my function. I will keep faith on my function recursive call, and it will return something that will be useful for me. And the third thing is defining the base case very clearly. These are the three things we should focus on whenever we are solving the problem of a BST question. Now let us talk about some other concepts. Now let us build BST. Now this is the given values, right? And using these values I am gonna build a BST. So to build a BST, what I am gonna do is that initially I am talking about the approach, how we are gonna build the BST. So what I will do is that initially at step 1 I will create a null node. Initially I am having a null node, right? And I will iterate through the given indexes of my array. This is my value array, and in this value array I will traverse through each and every element. So for this 5 I will make this fifth node, this 5 value, as my root node. So from this null I will change my tree to this. Now after changing, this will become my root node. Now after that I will iterate through its next element. In my values array I will iterate through the next index, and I will check this whether this value is greater than my root value. What is the root value? Root value is 5. So if my root value is greater than my element, then I will add that element on the left side. So I will add this one on the left side. Now after that I will iterate through its next element. So my tree will become something like this, 5 and 1. My tree will become 5 and 1, and the root node will be this. Now for this 3 element, what is the value, what is its comparison compared to my root node? My root node is 5 and the value is 3. It means that my value is less than my root node. So I will add on its left side. But on the left side I am having 1. So if 1 is the subroot node, then when compared to 1, what is the value? Whether it is greater or whether it is less, I will compare. You can see that 3 is greater than 1. So I will add on the right side of my tree. So my tree will become like this. After that I will iterate, and here my tree will look something like this. 1 and 3 will come on the right side of 1. Now here I am having 4. 4 is less than my 5 main root, and here again it is greater than the 1 value. It is greater than my subroot. So I will come on the right side. Now here you can see that 4 is again greater than my this third node. If I consider third node as a root, it is greater. So I will add 4 in this. On the right side of 3 I will add 4. Now after that I will iterate through my next element. Now what my tree will look like this 1, 3 and 4. Now you can see that here I am having 2, and 2 is less than 5, so it will come on the left side, and 2 is greater than 1, so it will come on the right side, and 2 2 is less than 3, so it will come like this. Now I will iterate through my last element. So my last element is 7, which is greater than 5. So my tree will be finally like this: 1, 3, 2, 4 and 7. So this will be my final root node. This will be my final BST. This is how I will create. I will iterate through each and every index, and as I iterate, I will compare my given array value, what are the elements present in my at that particular index in my value array, and my root node. I will compare, and recursively I will call for the next level. If there is a next level, I will recursively call, or else I will add that particular element on its respective position. Now let us code this thing. So what I will do is that first of all I will import java.util.star. After that I will create my class, public class Java programming, and after that what I will do is that first of all I will create a node class, static class node. In this, for a particular node, if you observe, we are having three things: node value, node left, node right. So I will create int data, that is nothing but my node value, after that node left part, node left, after that node right. After this I will create a constructor, public node. Here I need to pass some parameters. Node, here I will pass int data, int data. Here this dot data is equals to data. This will be my overall class. Now I will create a function, public class, to create my binary search tree. I am creating a function, public static node type function, node type return type, right? After it I will create function insert. So to insert elements in my tree I'm gonna create. Now what I will do is that I will pass my root node. After that I will pass my value, whatever the value I am having in my array, I will pass that. Now if my root is null, if my root initially my root is null, if my root is null, then I will add my root as root is equals to new node of value. Whatever the value user has given me, I will add that, and after that I will return. Here I need to give return root. I will return root. Now if my root is not null, then I have to check my conditions whether the given value is greater than my root.data or not. So if root.data is greater than my value, it means that my value is less than, then I need to add it on the right side. So this is the left side, I need to add it on the left side of my tree. So root.left is equals to, I need to recursively call, so I will call the same function insert, and I will pass root.left, and I will pass the same value. This is my function for adding on the left. If I have to add on the right, then it will come on the else path, and for this else path, right side adding, right side, that is root.right is equals to insert root.right, and that's all. And finally I will return my root value, that's all. This will be my insert function. Now I'm gonna create my function, public static main function, public static main string args, and here let me give a string array, and in the main function I'm gonna create my value, int value is equals to, and I'm gonna take whatever the values I have taken as an example. Now after that I will create my node, and I'm gonna initialize it with null. So root is equals to null. After initializing, after creating my root node with null, I will run a loop for int I is equals to 0, int I is equals to 0, and I should be less than value.length, and I plus plus. Now after this, what I will do is that I will call my insert function. I will call my insert function for my root node and my I value. Now let me create, to print the values, whatever the values I have created, right, I need to print it. Now for that I am gonna create a function, in order function. So public void, public static void type function in order, In this I will pass my root node int root. If my root is null, this will become my base case. If my root node is null, then I will return, basically return, come out of my function, return. Now what I have to do is that in order I need to call the left part first. So in order root dot left, after print system dot out dot print root dot data, after call for my right part, root dot right. This will become my what you can say, this will become my in order function. Now it is showing some kind of error in the main function, static void main. I need to give void main string args. Now let me save and run. Okay, my output is not printing. Here I need to store the root value, right? At each and every function call I need to change the root value. So if I don't change, then my root value will become null, and if I don't have anything, then I won't get any output. So I need to give here root. Now let me save and I should get the output now. Yeah, you can see that here. Let me give some space, root comma values of I. Okay. Here along with root I need to give not I but values of I. Right, now let me save and run. So you can see that we got the output as 1 2 3 4 5 6 7. So this is a sorted order. So this is how by this function we will create. What we have did is we have created the insert function, and in the main function I have created root is equals to null. After that I am calling my function and I am creating my BST. So this is how we will create BST in our code. Now let us talk about other things. Now let us talk about how we're gonna code the searching operation in a BST. I said that searching operation is much more efficient in a BST. Now let us talk about how we're gonna do this. So let us say that for this particular tree my BST, my key value is 1. Now what I will do is that first of all I will compare whether my root value is greater than my key value. If it is, then I will come on the left subtree part and I will check. I will call my recursive function for the left subtree, and for the left subtree I will check. If my k value is greater than root, then I will come on the right subtree and I will call the recursive function for the right subtree RST part. If my key is equals to root, this is very similar to binary search, but instead of linear data structure we are calling for hierarchical data structure. That's all. There is no you can say difference at all. Both are basically same. So if my key is equals to root, then I will basically print, or you can say return true. If I didn't reach the case and my number of levels are completed, then I will return false. So this is how searching will work. And one more thing is that talking about time complexity, let's say I got my output somewhere in the middle, then for that particular thing my time complexity will be big of h, and h is the height of the tree. And if I get my element in the right in the middle or somewhere in the average cases, then my time complexity will become big of log n. And if I got the time complexity on the last element on the leaf node, then my time complexity will become big of n. So this big of h can be log big of n, or this can be big of n based on the cases. And this big of h on average cases I will get log n, on worst cases I will get big of n. You need to remember that big of h value in worst cases will be big of n, and in average cases I will get big of h as my output, big of log n as my output in average cases, and for worst case my time complexity will become big of n. You need to remember this also. And this big of h value is not fixed. It will change time to time based on the case, whether it is a best case, whether it is a average case, whether it is a worst case, it will change time to time. Now let us talk about how we're gonna code this. Let us code this thing. I hope you have understood the logic. Now let us code this thing. I will create a function, public static boolean type function, search boolean search SEARCH search. In this I will pass my node root value and key value, int key. In this I will check first of all what will be my base case. My base case will be if my root is null, that is I am reaching a null case, then I will immediately return false. It means that my node, my root, whatever the key I am passing, it is not present in my BST. Now after that what I will do is that I will check if my root dot data is equals to key, then I will immediately return true. Else if my root dot data is greater than key. If my root is greater than key, then I will go to the left part. I will call recursively for the left part. So I will return search function for the left part. So root dot left, and I will pass the same key. Else what I will do is that if else I will call the same recursive function for the right part, search root dot right. So this is a search function. This is how I will perform search in my BST. Now what I'm gonna do is that I will call my search function for root node, and let's say I'm passing 5. So these are the elements, right? These are the elements present in my BST. Now if I call search for the key 5, then my output should be true. Now let me save and run. So and along with that, whatever the value I am returning, I need to print that value. So I will print whatever the returned value is. Here I will print. Now let me save this and run. So you can see that I got the output as true. Now if I pass something like let's say I am passing something 12, I am passing 12. Now if I pass 12, we already know that in the values array we are not having 12. So in the create BST, I won't have any value that is equal to 12. So if I run this, then my output should be false. Now let me save. You can see that my output is false. So this is how we will perform search operation in a BST. Now let us talk about other things. So we have seen what is a BST, properties involved in it. We have built BST, performed search operation. Now we are going to talk about how to delete a particular node in my binary search tree. So to delete a particular node, let's say I want to delete here in this BST, I want to delete 20, right? I want to delete 20 node. Now my question is that whether this particular 20 value is present in my BST or not. If it is present, then I can able to delete. If it is not present, then I can't delete. So the first step in deleting a particular node in my BST will be find node. Find the given value node, and if it is present, then I will check these different cases. These are the 3 different cases that we will discuss in detail. If it is not present, then I will show to my user that that particular values didn't exist, and I will say that it is not present in my BST, and I will return and come out of my program. So this will be my overall approach of my deleting operation. Now let us talk about deleting operation cases. If the node is present, then we will get 3 different cases, and these 3 different deleting operation is kinda, you can say, complex and at the same time very interesting. You can see that search operation is very easy, building is very easy. Now this is going to be a little bit complex, but it is easy also, right? If we understand, it will become easy. Now for deleting, we will get 3 cases, and these 3 different cases are: if my given node is a leaf node. If it is a leaf node, then I will directly delete it, right? And the second case will be if it is having a left child. If it is having a left child on the right side, or if it is having a value on the right side, then I will get some other conditions. And the third thing will be if it is having both child, if it is having a right child as well as a left child, then we will follow some different procedure based on the different cases. Right now let us talk about the first condition, that is no child condition. If let's say in my tree, this is a tree, right? I'm considering here I need to create a BST. So 4 1 0 and 5. Now I'm taking this as an example. So I want to create the element node. I want to delete an element which is having 5. Now you can see that the 5th node is not having any values. So what I will do is that first of all I will return that particular node, and after directly return null, right? Directly return null to my present node. This will be the simplest approach. And this is going to be like very easy. What I will do is that, let's say this is my tree, right? So for this particular node, it is pointing to null. So what I will do is that I will make this 4th node directly points to null, and this connection will get directly automatically deleted by my Java garbage collector. My Java garbage collector will automatically delete this element. So what I will do is that for a particular node, if it is a leaf node, then what I will do is that its parent element, instead of pointing to this leaf node, it will point to its null value. It will directly point to a null value, and because its parent is pointing to null, this node will get automatically deleted by my Java collection framework or Java garbage collector. So this is a basic approach. I hope you got the logic. Now in the second case, let's say my tree is having some values. Taking the same tree 1, 5, I'm taking we have to create a BST, right? 4, 3, and 4, 3, let me give here 6, 7. So you can see that, let's set my key value, my key which the element which I'm gonna create delete is 6. So what I will do is that if it is having a left or a right child, here you can see that this 6th node is having a right child, one right child. If it is having one right child, then what I will do is that its parent referral, instead of pointing, now you can see that this 5 is pointing to 6. Instead of pointing to 6, what I will do is I will directly point to its children. This element children, I will point directly to its children's value, and because this node, 6th node parent is pointing to its direct children, my Java garbage collector will automatically delete this node. Got my point? Up to now I hope it is very clear that if there are no children, then directly delete the element. If there are children, then that particular node which is we deleted, its parent referral, instead of pointing to this element, it will directly point to its children. Because its parent is directly pointing to its children, my Java garbage collector will automatically delete this node. Got my point? Now the third case, and this is a little bit confusing, or you can say complex case, which is what I will do is that here let us say that this is my given tree. I am creating a tree, let's say at 8 and 5, 3, 1, 4, 6, 10, 11 and 14. So this is the overall tree, right? Now let's say that I wanna delete 5. I wanna delete 5 from my tree. So what I will do is that replace the in-order successor and delete the node for the in-order successor. What this two lines means, let us understand this. If we understand the third case, we have understood the two cases, very simple cases. If we understand this third case, then we can easily code overall approach. So what I will do is that first of all I will take the in order sequence for this particular tree. So if I print the in order sequence, my output will be 1, 3, 4, 5, 6, 8, 10, 11, 14. So this is my in order sequence, right? And I will check what is the element that I am going to delete. So this is the element which I am going to delete, right? So after seeing this element, what I will do is that I will see their next element, next successor. You can see that the next successor is 6. Its next successor is 6. So what I will do is that I will copy this element value and I will paste it here. So here you can see that I am having 6, right? So if I will see its 6 value and I will replace this 6 value here. Now after replacing this 6 value, I will delete this element because this is a leaf element and I know how to delete a leaf. That is my case 1. So I will directly delete this element and my tree will become something like this: 8, 6, 3, 1, 4 and 10, 11 and 15. So this is how I'm gonna do it. I will check its next successor, and in the next successor, what is the least value? Here you can see in the whole array, what is the least value? I will take that value and I will replace it with my current value. And after replacing, I will delete that duplicated element. Here you can see that after replacing 6, I have deleted 6. right? Whatever the duplicated element I am having in the successive part, I will delete that. I hope you got the logic. If you don't, then replay this thing and listen to this again. And I will tell you again one more time that I am having a tree, right? And I am gonna delete a particular node which are having right tree and left subtree. So what I will do is that I will check in order successor, and in the in order successor, let's say that this is the element, 5 is the element I am going to delete. So for this particular tree, for this particular node, in the right subtree, what is the least element? I will choose the least element and I will replace its value with my element value which is to be deleted. Here you can see that in this array the least element is 6. So I have taken this value and I have replaced it with 6. And after replacing 6, I am deleting this element and my in order will become 1, 3, 4, 6, 8, 10, 11, 14. So this is what I am gonna do, right? So let's say that this is my tree. This is my tree. Here, this is my right part. Right, this is my tree. Now I want to delete this particular root node or whatever the node it is. I want to delete this. So what I will do is that I will check its right least element, and just observe that in this tree on the right side, where I can find my least element. I can find my least element on the left part. So I will go to its left part, and finally here I will find the least element, and that element will get replaced by this, and I will delete this element. I hope you got the logic here. Now let us code this thing. Now I will create my function public static and I will return node. After deleting that, I will return that node. So delete. Here I will pass node root, after it int value. Here I will check if my root value, if my root dot data, I need to search the element, right? First I need to search the element. If it is present, then I will go further for deletion operation. If the element is itself not present, then I can't delete it, right? So I need to search, I need to perform search operation first. So if my root dot data is less than my value, then I will call for the right part. Root dot right is equals to same delete operation for the right part of my tree. So root dot right, same value. Else if my root dot data is greater than my value, then I need to search it on the right side. So root dot left is equals to delete recursive function call for my root dot left part and my value. Now the else condition will be if I found my element. This is my hooray condition, right? Hooray. So if I found my element, then what will be the case? I need to check the case 1. The case 1 will be if it is a leaf element, it means that it is not having any child. Then what I will do is that I need to check whether that particular element is a leaf element or not. How I can check that? If my root dot left is equals to null, and if my root dot right, if a particular leaf node is a root element, is a leaf element, then it will have null on the right side and it will have null on the left side. So if root dot right is equals to null, if these both cases are true, then what I will do is that I will return null. It means that I am indirectly deleting that element. Now checking the case 2. The case 2 will be if a particular element has either left child or a right child. It means that it is having only one single child, right? So for that, what I will do is that I will check whether it is having child on the left side or whether it is having child on the right side. So if root dot left is equals to null, if this is the case, then it is having child on the left side. So what I will do is that I will return root dot right. I will return root dot right. Else what I will do is that I will check, I will return root dot left. Now third case. So this is the important case here, that is if a particular node having both left subtree and the right subtree, then what I have to do? I need to check its next successor, in order successor. So I'm gonna create a node which will keep track of in order successor. So this will give me find my in order successor, find in order suc. This will find the in order successor. Here I will pass root dot right. First of all, I will pass the right side, and I will add root dot data is equals to in order successor dot data. From the logic what I have extracted. So in the, let's say this is my element which is to be deleted, and it has some left part and the right part. So what I have to do is I have to go on its left part, and in the left part, which is the least value, I will take the least value and I will replace this node with this least value. So this is what I'm gonna do, right? So I have gone on the right side of my tree for that particular in order successor. Now what I will do is that I am storing its data in my root data. After that, I will change root dot right is equals to delete and root dot right value, and I will pass here, instead of value, I need to replace the value, right, with the least value. So is dot data, in order successor. So this in order successor will give me the least value present on my right side of the tree. I hope you are getting it, right? This is what I'm gonna do. So I will pass here, and finally I will return my root. Now let us create this find in order successor. So I will create a function, public static node type function. This will also return a node find successor. Here I need to pass my node root node value, right? So node root. Now here I need to check, I need to take the least value which is present on the left subtree. So I will run a loop while my root dot left. So to take the least value, I said that on the left side I will have, in a BST I will have the least value on the left side. So I will take the least value by going on the left side until I hit my null case, until my left is not equals to null. If this is not null, then I will keep on going on the left side. So I will change root is equals to root dot left. After that I will return root value. This will be my function. Now let me save. So in this I have created my find order successor, and after that in the main program what I am doing is that here I am checking. First of all, I am calling in order, and these are the elements I have created. As I write in this question, these are the elements I have created, and after creating my elements, I am calling in order first. After that, printing a next line, and after creating that, I am calling my recursive like delete function for sixth element, and again after deleting that element, I am printing the elements, whatever elements present in it. Now let me save and run. So here you can see that before deleting, these are the elements. Now after deleting 6, this is how my BST is formed. So this is how we will delete the elements in my BST. I hope you got the logic. So what I did is that first of all I have created delete function, and in the delete function I am checking whether the element is present or not. If it is not present, then I will return null. If it is present, then what I am checking is I am checking three different conditions, and in the third condition I am finding the least value on the right side, the next successor of my BST. And how I am finding, this is how I am finding. I am going on the left side of my right subtree. I am going its left side, right? And after getting the least value, I am returning it. And after returning, I am replacing that least value with my data, and after that I am deleting the root value. This is what I am doing. Now this is the overall working. I hope you have understood. Now we will stop here our lecture, and in the next part we will do some questions.